Greetings, and thank you for joining us on the Sleep Science Top 1. It's wonderful to have you here. It could be that today has felt quite lengthy. Perhaps you find comfort in drifting off to sleep while contemplating stars, galaxies, and the serene enigmas of the universe. Regardless of the circumstances, this evening's adventure is dedicated to you. At this moment, there are no actions required from you. Allow your body to relax and your mind to unwind. Your mind wanders. Tonight, we embark on a journey through the very fabric of the universe. Not merely a single galaxy or star, but the immense, ever-expanding entirety. We will transition smoothly from one fact to another, exploring topics such as black holes, ancient light, dark matter, and far-off galaxies. You might find a few things unexpected. Some may linger by your side, resembling a soft whisper as you drift into slumber. If these soothing explorations bring you peace, don't hesitate to like and subscribe. It assists others in discovering their path here as well. All right, if you're prepared, let's get started. The universe could be more ancient than we previously believed. The latest estimates suggest that the universe is approximately 13.8 billion years old. The figure is derived from observations of the CMB and the rate at which the universe is expanding. However, there are discrepancies among the methods. Certain observations of ancient stars and galaxies indicate that they might be older than the estimate permits. Some individuals challenge the presumed rate of expansion or propose that dark energy might be evolving over time. The existing tensions remain unresolved, and the majority of astronomers continue to endorse the 13.8 figure. However, the inquiries persist. Is it possible that the universe is older? Did we overlook something essential? What we perceive as the beginning might merely be a segment of a more intricate and unusual narrative. Countless interstellar planets wander through the vastness of space, untethered to any stars. Some planets do not follow a path around stars. Some drift freely, unanchored in the vastness of the galaxy, lacking the warmth of a sun or the illumination of a sky. These interstellar planets might have formed in a typical manner, only to be expelled from their star systems due to gravitational turmoil. Some may have developed independently, akin to unsuccessful stars. They are shrouded in darkness, frigid, and almost undetectable unless they move against the backdrop of stars or emit a subtle glow in infrared. Astronomers estimate that there could be billions of them in the Milky Way galaxy, possibly even exceeding the number of stars. Every single one exists as a quiet realm, floating in shadow, rotating solitary in the immense voids that lie in between. There are no sunrises or sunsets, only an infinite night illuminated by the faint glow of distant stars. The universe might undergo endless cycles of recycling itself. The standard model of cosmology outlines a universe that originated from the Big Bang and is set to keep expanding, potentially for eternity. However, certain theories propose an alternative narrative, suggesting that the universe experiences cycles of expansion and contraction. In these models, the universe does not conclude with a cold fade or a final crunch. Rather, it starts over. Upon reaching a specific threshold, it may contract, folding inward, before springing back into a fresh expansion. Every cycle has the potential to erase the previous frameworks, while retaining faint remnants of their existence. These concepts are hypothetical, yet captivating. It is proposed that the universe might not possess a definitive beginning or end, but rather a rhythm that extends over incomprehensible lengths of time, a single universe generating another, repeatedly. The earliest light observable to us originates from 380,000 years following the Big Bang. Prior to that moment, the universe existed as a radiant mist, so intensely hot and compact that light struggled to journey far without dispersing. However, as it grew and cooled, it arrived at a pivotal moment. Atoms came together, the mist dissipated, and light was abruptly liberated to travel. The CMB is that ancient light, and we are still able to detect it today. This is the most ancient direct signal in the universe, originating not from stars or galaxies, but from the universe itself during its initial moments of becoming transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is subtle, yet constant, a gentle illumination that holds the essence of the universe's initial brilliance. Certain stars possess planets that are composed predominantly of diamond. In some solar systems, the chemistry varies significantly from what we know. When a planet develops with a higher concentration of carbon compared to oxygen, and the pressures reach significant levels, an extraordinary phenomenon can occur: the formation of a carbon planet. Astronomers have identified at least one candidate, a dense planet orbiting a pulsar, probably the remnant of a deceased star. Considering its mass, density, and composition, the whole planet could be a crystalline structure of carbon, effectively making it a colossal diamond. The heat is overwhelming, and from a close perspective, it wouldn't resemble a gem at all. However, far below the surface, vast carbon structures may extend for thousands of kilometers. These unusual worlds are rare, yet they serve as a reminder of the incredible diversity that exists within the universe. A celestial body composed of solid material. A celestial body composed entirely of gaseous elements. And at times, a planet crafted from crystal. The universe might lack an edge, presenting only infinite curvature. It's easy to envision the universe as having a limit, a boundary we could touch if we journeyed far enough. However, it appears that space does not function in that manner. General relativity posits that the structure of space is influenced by what it contains, and existing evidence indicates that the universe may be infinite or so extensive and curved that it ultimately reconnects with itself. If that is indeed the case, one could theoretically journey in a straight line indefinitely and ultimately find oneself back at the original point, not by encountering a barrier, but by navigating through the curvature of space. This resembles the way that journeying across the Earth does not uncover a boundary, only a sphere. The cosmos might operate similarly, but on a vastly larger level. Not boundless in space, but boundless in exploration. There was a time when the Sun had a twin, and it's possible that it still exists somewhere in the cosmos. Certain astronomers propose that our Sun had a twin, a companion star, that originated from the same cloud of gas and dust more than 4.5 billion years ago. A multitude of stars are forming in pairs, and it stands to reason that our Sun was likely no different. If it were real, this missing sibling would have long since floated away, drawn apart by the gradual gravitational pull of the Milky Way galaxy. It could very well be out there, traversing the galaxy on an alternate trajectory, currently unseen by our eyes. Certain theories suggest a connection between this twin, referred to as nemesis, and enigmatic extinction patterns on Earth, although there is no concrete evidence to support this claim. Yet, the thought remains that our Sun, constant and solitary in our heavens, might have once emerged alongside a quiet companion, now long lost to the cosmos. A single raindrop from a neutron star would have a mass greater than that of Mount Everest. Neutron stars represent the collapsed cores of massive stars, serving as incredibly dense remnants that remain after the cataclysmic events of supernova explosions. They measure approximately 20 kilometers across, yet their mass surpasses that of the Sun. The material contained within is so tightly compressed that just 1 teaspoon of it would have a mass of billions of tons. Envision a solitary raindrop composed of neutron star material. It would possess a weight greater than that of any mountain found on Earth. Such a level of density challenges what we typically encounter in our daily lives. Atoms are compressed to such an extent that electrons and protons combine to create neutrons, resulting in a superfluid neutron soup. Neutron stars are remarkable entities, compact, shadowy, dense, and rotating at high speeds. Yet within their silent gathering, they carry the remembrance of stellar collapse, a concluding phase where matter transforms into almost pure gravity. Light from a single galaxy can arrive at our location from various angles. At times, light may not follow a direct path. In areas of the universe where gravitational forces are particularly intense, such as near large clusters of galaxies, the fabric of space-time bends. This curvature alters the trajectory of light, similar to how glass refracts a beam. Gravitational lensing is the term used to describe a phenomenon where, intriguingly, we can occasionally observe multiple perspectives of the same distant galaxy from various angles. These visuals may manifest as arcs, smudges, or even full rings. They aren't duplicates in space. Rather, they are duplicates in vision, representing distinct paths that light has traversed through the distortions of space-time to arrive at our eyes. In some exceptional instances, astronomers have detected the same supernova detonating multiple times as its light traveled via various gravitational pathways. It serves as a gentle reminder that in the vastness of the universe, even light can wander, take a more circuitous route, and ultimately return to its origin. The initial stars could have radiated light 1,000,000 times more intensely than our Sun. The initial stars were truly unique compared to what we observe now. Originating from the primordial hydrogen and helium that remained after the Big Bang, these stars, known as population 3 stars, probably emerged without any metals, resulting in their massive, hot, and ephemeral nature. Certain objects could have been hundreds of times more massive than the Sun. They would have consumed their fuel rapidly, radiating a brilliance far exceeding that of our own Sun, before ultimately collapsing in breathtaking explosions after merely a few million years. Although none of these stars exist today, their fleeting existence transformed the universe. They formed the initial heavy elements, illuminated galaxies, and laid the groundwork for all that came after, including our existence. Their light has faded, yet their fingerprints linger in the chemistry of ancient gas clouds and in the subtle architecture of the early cosmos. As you sleep, dark matter flows through your body. As you remain motionless, dark matter glides quietly in your vicinity. It's not an unseen fog. It is a type of matter that does not engage with light, nor does it reflect, emit, or absorb it. However, it possesses mass and reacts to gravitational forces. The galaxy we inhabit is enveloped by an immense halo of dark matter. As Earth traverses this halo, it is believed that trillions of dark matter particles pass through every square centimeter of your body each second. They do not come into contact with your atoms. They leave no evidence behind, yet they linger, ethereal, always around, and crucial. In the absence of dark matter, galaxies would fail to maintain their cohesion, cosmic structures would not emerge, and the universe would present a vastly different landscape. The composition of dark matter remains a mystery to us. However, we are aware of this detail. It exists within your realm, flowing through you, quietly and perpetually, even while you rest. There are galaxies that emit light even in the absence of stars. In the serene expanses of the universe, astronomers have uncovered galaxies that radiate light, yet hold a scant number of stars. These ethereal systems are abundant in gas and dark matter, yet display minimal to no signs of star formation. Some might have lost their stars due to intense gravitational interactions. Some individuals might not have created many stars whatsoever. Some are almost undetectable, revealing themselves only in specific wavelengths of light, thanks to imperfections in extensive sky surveys. These galaxies question our previous understanding of the processes involved in galaxy formation and evolution. If they possess an abundance of dark matter, what is preventing them from forming stars? If they once had stars, where have they vanished to? These dim, quiet systems drift through space like the remnants of a bygone era, serving as reminders that not every galaxy is ablaze with brilliance. Some merely float, unnoticed and without resolution. A cold spot exists in the universe that defies expectations. In the CMB, the subtle illumination remaining from the Big Bang, there exists a section of the sky that is notably cooler. It's not merely a bit cooler than its environment. It's considerably colder and much larger than researchers anticipated. This cold region extends across hundreds of millions of light years, and its existence doesn't entirely align with the uniform randomness anticipated from the physics of the early universe. Some believe it could be the mark of an immense cosmic emptiness. Some speculate whether it might suggest something even more peculiar, such as the merging of our universe with another during the initial phases of inflation. No explanation thus far completely aligns. The cold spot continues to be one of the most subtly disconcerting enigmas in cosmology. Not an overt anomaly, but a faint indication that aspects of our universe might not align with our understanding. The moon is gradually drifting away from us. Annually, the moon moves a slight distance further from Earth, approximately 3.5 centimeters. Your fingernails grow at approximately that rate. This gradual withdrawal has been occurring since the moon's formation approximately 4.5 billion years ago, at which time it was significantly nearer, and a day on Earth lasted only a few hours. The reason is tidal friction, as the moon exerts its gravitational influence on Earth's oceans and Earth rotates below. A subtle transfer of energy slowly propels the moon further away in its orbit. It unfolds in silence, a steady progression that may go unnoticed in the span of a human life, yet becomes undeniably clear when viewed across the vastness of time. In a distant future, Earth and the moon could reach a state of tidal locking, consistently presenting the same side to one another. At this moment, it continues to elude us, gradually fading as we revolve under its far-off, radiant glow. Binary stars can exchange their outer layers, much like dancers in close contact. In certain binary star systems, the two stars orbit in such proximity that their outer layers start to make contact. As they develop, one star can expand and transfer matter to the other, resulting in a gentle, swirling transfer of material. At times, the transfer proceeds in a smooth and consistent manner. At other moments, it can cause flashes of light, swift spinning, or even a total fusion. The physics may be intricate, yet the visual is surprisingly elegant. Two stars entwined in their dance, revolving closely enough to touch and merge. One star might ultimately be reduced to a radiant core, whereas the other could become enlarged and more abundant. Their destinies are intertwined. Among the most extraordinary objects in the universe, such as specific supernovae or compact pairs of neutron stars, originate from these serene and intimate binaries. A gentle reminder that in the vastness of space, even stars have the capacity to share, transform, and occasionally come together in harmony. The vacuum of space is not entirely devoid of substance. Even in the most profound and shadowy corners of space, distant from any star or galaxy, the universe is never genuinely devoid of substance. In the realm of quantum physics, the vacuum is not empty, but rather a dynamic sea of activity. Small particle-antiparticle pairs emerge briefly and disappear in an instant. Quantum fluctuations occur constantly, everywhere, forming a sort of restless backdrop to reality itself. They have the ability to sway the movement of particles, impact the dynamics of fields, and play a role in the energy present in vacant space. This contributes to the emergence of dark energy, the enigmatic force that propels the universe's expansion at an accelerating rate. When we envision deep space as being silent and still, that portrayal is only partially accurate. Underneath the stillness, there exists a choreography of chances, a subtle resonance of emergence and vanishing, perpetually lurking beneath the facade of emptiness. Time can progress at varying speeds across different areas of the universe. Time is often perceived as a constant, a rhythmic ticking that moves uniformly for all individuals. However, in truth, time is intricately connected to gravity, motion, and the very structure of space-time. In areas with intense gravity, such as those close to a black hole or a compact galaxy cluster, time experiences a slowdown compared to regions where gravity is less pronounced. This is more than mere theory. Experiments, satellites, and atomic clocks have all confirmed this information. However, certain cosmologists speculate about the possibility of time varying on even grander scales. Is it possible that various regions of the universe could experience time at slightly different rates because of the way the universe expanded in its initial moments? The concept is theoretical, yet it presents unusual opportunities. In a universe shaped by relativity, time itself might not be a fixed concept. It might extend, decelerate, or curve, subtly molded by the environment it traverses. The Milky Way galaxy possesses a concealed halo that surpasses the size of the visible galaxy. Images of the Milky Way galaxy reveal a radiant spiral, with stars, dust, and gas elegantly organized into stunning arms. Yet encircling this well-known structure is an immense and largely unseen entity, the galactic halo. It is an enormous sphere composed of diffuse gas and dark matter, stretching well beyond the visible boundary of the galaxy and reaching distances that far exceed the width of the disk itself. This halo is composed of ancient star clusters, wandering stars, and significant quantities of invisible mass. It is bound by gravity, molded by a history of impacts and unions, and contributes subtly to the stability of the galaxy. While it remains invisible to our eyes, we deduce its existence from the movement of stars and the curvature of light. The Milky Way galaxy is, in fact, merely the luminous core of a far grander entity, a radiant heart enveloped in unseen embrace. We have observed light emanating from a galaxy that formed merely 200 million years following the Big Bang. The age of the universe is approximately 13.8 billion years. However, light does not travel at an instantaneous speed. It travels through the vastness of space, elongated and decelerated throughout its journey. This is the reason we observe galaxies not in their current state, but as they existed in the distant past. Astronomers utilizing the JWST have recently detected light from a galaxy that formed merely 200 million years following the Big Bang, a fleeting moment in the vast timeline of the universe. The light has journeyed toward us for over 13.5 billion years. The galaxy is diminutive, dim, and rudimentary, yet it contains hints about the formation of the earliest structures. Watching it feels like peering through a small opening into a realm we were never intended to witness, the cosmos in its formative stages, as shadows slowly started to yield to the light of stars. The vast arrangement of the universe resembles a neural network. A surprising pattern emerges when astronomers chart the locations of galaxies over vast distances. Galaxies are not dispersed haphazardly. Rather, they group together along elongated, thread-like filaments, with expansive, empty spaces known as cosmic voids in between. This vast network spans billions of light years and is often referred to as the large-scale structure. It's quite unsettling that when you zoom out sufficiently, this structure resembles a neural network remarkably similar to those in the human brain. Clusters of galaxies resemble neurons, while the filaments serve as axons linking them together. Certainly, the similarity is entirely based on structure. The universe does not possess thought, yet it remains subtly lovely to reflect upon. The most massive structure we are aware of, along with the one within your own consciousness, formed by completely distinct principles, can surprisingly appear quite similar. Stars have the ability to produce sound even in the emptiness of space. In the vacuum of space, sound cannot travel as it does on Earth due to the absence of air. However, stars do produce sound, with deep, slow vibrations that move through their internal gases, akin to seismic waves passing through a planet. The pressure waves cause the star to pulse and oscillate, and researchers can identify them by monitoring slight variations in the star's brightness or surface movement. Astroseismology is the field that focuses on this subject, which translates to the seismology of stars. Every star possesses unique internal frequencies, akin to a fingerprint, shaped by its size, structure, and age. Through the observation of these remarkable vibrations, researchers are able to gain insights into the inner workings of stars and uncover the processes occurring beneath their surfaces. It resembles a form of cosmic echolocation, allowing one to perceive the melodies of stars spanning light years, even when the tune remains inaudible to human senses. Certain stars have ages that surpass those of the galaxies they inhabit. Galaxies are not formed in a single moment. Over time, they come together, integrating with smaller systems and attracting stars and gas from surrounding areas. Some stars within a galaxy may be older than the galaxy's existing structure. It is possible that they originated in smaller galaxies that eventually combined to create a larger galaxy. These ancient stars typically reside in the outskirts or within globular clusters, which are tightly bound groups that orbit at a considerable distance from the galaxy's core. Certain ones date back over 13 billion years, almost as ancient as the universe itself. They possess the chemical signature of a younger universe, characterized by a scarcity of heavy elements and the presence of only the simplest atoms. These stars resemble fossils, silent witnesses from a time before the galaxy was fully formed. Their illumination is aged. Their narrative started long before much of what we understand had even taken shape. Some galaxies exist without dark matter, and the reasons for this remain a mystery. Dark matter is believed to be the unseen force that binds galaxies together. This clarifies the reasons behind the faster-than-anticipated movement of stars in the outer regions of galaxies, as well as the clustering patterns observed among galaxies. However, in recent years, astronomers have discovered galaxies that appear to challenge this rule. Galaxies that appear to function without any dark matter whatsoever. Their stars appear to move as if only the visible matter exists. This finding came as a surprise, and it doesn't align smoothly with existing frameworks. Certain scientists believe that dark matter was removed during previous collisions. Some people question whether we truly grasp the nature of dark matter. Interestingly, these unusual galaxies imply that the universe continues to hold mysteries, and that what we consider to be universal might not actually be universal in nature. The sun resonates with a colossal, echoing chime. Within the core of the sun, sound waves travel through the plasma, reflecting off various layers and creating a gentle, ongoing vibration throughout the entire star. These waves differ from the sounds we perceive with our ears. They are waves of pressure, quiet, gradual, and well beneath the range of human perception. However, utilizing sensitive instruments, researchers are able to identify them and employ them to investigate the internal structure of the sun. This area of study is known as heliosysmology. Through the observation of solar oscillations, researchers are able to chart the activities occurring beneath the sun's surface, including its density, rotation, and the concealed movements of hot gases. The sun, in this way, functions as a grand musical instrument, intricate, expansive, and perpetually in performance. We simply require the appropriate instruments to hear. The sounds we perceive aid in our comprehension of not just the sun, but also stars throughout the universe. Galaxies adhere to filaments composed of an unseen substance. The largest structures in the universe are not composed of stars or gas. They are influenced by an unseen force, dark matter. Over billions of years, this dark matter developed into vast filaments that extend across the cosmos. Galaxies typically form and travel along these filaments, resembling beads strung on a line. While the filaments themselves are not directly visible, we can deduce their presence by examining the clustering of galaxies and the way light is distorted as it travels through these areas. The filaments can extend across hundreds of millions of light years, linking immense clusters of galaxies. In the spaces between, vast emptiness prevails, with scarcely any matter present. The dark matter filaments serve as an unseen framework for the visible universe, influencing the growth of galaxies and their trajectories. Despite our advancements, the nature of dark matter remains a mystery. The framework exists, vast, hidden, and silently binding the cosmos as one. Space has the ability to expand at a rate that exceeds the speed of light. Under typical conditions, nothing can travel faster than light. However, space itself does not adhere to that rule. In the initial moments following the Big Bang, the expansion of space occurred at such a tremendous rate that certain areas of the universe were separated at speeds exceeding that of light itself. This was not movement through space. It was the growth of the very fabric of space. Even now, far-off galaxies aren't speeding away due to their rapid movement through space. They are moving away as the distance between us and them increases. If they are sufficiently distant, that stretching causes them to move away at a speed greater than light, which is the reason we will never observe them again. It doesn't breach the laws of physics. Rather, it's a subtle outcome of the way space operates on a grand scale. The universe can take its time. It steadily grows, with a quiet determination, surpassing our ability to keep pace. The solar system navigates through space in a helical spiral pattern. One can easily envision the planets revolving around the Sun in orderly, two-dimensional circles. However, if you take a step back, a more peculiar picture begins to unfold. The Sun is in motion, traveling around the center of the Milky Way galaxy at almost 1,000,000 kilometers per hour. As it progresses, the planets trail along, not merely orbiting the Sun, but spiraling through the cosmos in its wake. The motion together forms a helical design, resembling a corkscrew or a spiraling ribbon. All things are in flux. The celestial bodies, the solar orb, the luminous stars, the vast galaxy. In the vastness of space, there exists no stillness, only a fluid and unending movement. As we rest, we are moving in gentle spirals through a dynamic galaxy, enveloped in a complex web of orbits, engaged in a grand dance that remains imperceptible to us. Even emptiness possesses a temperature. As you venture far from stars, planets, and galaxies into the vastness of intergalactic space, you will encounter an expanse that appears to be sheer emptiness. However, it is important to note that even the vacuum possesses a temperature. The temperature is approximately 2.7 Kelvin, only a few degrees above absolute zero. The origin lies in the CMB, the residual light from the Big Bang, which has been elongated and cooled over billions of years due to the expansion of the universe. This subtle radiation permeates the whole universe. Wherever you find yourself, it will be present. The faint thermal signature of the early universe remains, still present, still detectable. In the times ahead, it will become even cooler. In several trillion years, the universe could come close to absolute zero, yet it will never fully attain that state. For even in the greatest void, the resonance of warmth persists. Quantum fluctuations could have influenced the formation of the entire universe. At the tiniest levels of existence, much smaller than atoms, the universe acts in ways that are not easily anticipated. Small, random variations in energy can emerge and disappear in a moment because of the inherent uncertainty present in quantum physics. Many cosmologists suggest that those brief random blips could have been amplified during the universe's initial moments via a process known as inflation. As the universe expanded at an incredible pace, minuscule variations were magnified to grand scales. The variations gave rise to the foundations of order, the points where matter would gather, where galaxies would emerge, and where stars would ultimately burst into flame. To put it another way, the vast architecture of the universe, including galaxies, filaments, and voids, could all originate from transient random occurrences at the tiniest scale. All that we observe today emerges from the quivering void. Stars nearing the end of their life can exhibit pulsations reminiscent of heartbeats over the span of millions of years. Not every star concludes with an explosion. Some fade at a slower pace, and in their concluding phases, they may pulsate, expanding and contracting in rhythmic cycles. These stars, known as variable stars, exhibit fluctuations in brightness over time. At times, The alterations occur in a consistent and rhythmic manner, echoing the gentle pulse of a heartbeat. The pulses result from alterations in the star's outer layers, where gases expand and cool, followed by a collapse and subsequent heating once more. Certain stars exhibit a pulsing behavior every few days. Some individuals require months or even years to finish a cycle. The pulsating stars have served as a means to gauge distances in the cosmos, as their patterns of pulsation correspond to their actual brightness. They also act as subtle reminders that even in death, stars can continue to mark the passage of time, not with a ticking clock, but with a deep, measured breath spanning the vastness of cosmic time. Earth resides within a massive bubble of heated gas. If you were able to perceive the hidden wavelengths of light beyond the limits of human vision, you would discover that our solar system resides within an immense, luminous bubble of heated gas. The local interstellar bubble is a vast region, extending for hundreds of light years in all directions. This bubble is believed to have been shaped by ancient supernovae, the explosive stars that sent shockwaves through the surrounding gas, heating and clearing it away. At this moment, our solar system glides serenely through a sparse area, enveloped by a layer of warmer gas and dust. It poses no danger. It's not an experience we can sense. Yet it exists, a subtle space enveloping us, originating from past turmoil, now woven into the serene tapestry of our cosmic surroundings. A vast, empty region lies behind the Great Attractor. The Great Attractor is an enigmatic gravitational phenomenon, a vast area of space with such immense mass that entire clusters of galaxies, including our Milky Way galaxy, are gradually being drawn towards it. Yet, beneath this vast accumulation of matter exists an even more peculiar area, referred to as the dipole repeller, where the expanse of space seems remarkably devoid of substance. It's more than just a section with a reduced number of galaxies. It's an immense, celestial expanse, extending for hundreds of millions of light years. Strangely, its void appears to repel galaxies. The Great Attractor and the dipole repeller engage in a subtle gravitational tug-of-war, influencing the dynamics of our local universe. We are compelled to move ahead by an invisible force, while simultaneously held back by the void that lies beyond. It serves as a reminder that in the universe, the elements of presence and absence can influence the journey we undertake. Neutrinos move quietly through the Earth and through you. At this very moment, countless particles known as neutrinos are moving through your body, and you won't even notice them. Neutrinos are remarkably lightweight. Neutral particles generated in vast quantities by the Sun, supernovae, and even the primordial universe. They have minimal interaction with ordinary matter. They can pass right through a planet or your whole body without leaving any evidence behind. Certain particles traverse detectors located deep underground, where infrequent collisions provide valuable insights for our research. However, the majority go by without drawing any attention. These particles exist in every corner, continuously moving through both space and matter without making a sound. They travel at almost light speed, yet they rarely make contact with anything. The cosmos is brimming with activity. Even when all seems quiet, the largest stars can collapse straight into black holes without any explosion. We frequently envision the demise of a colossal star as a dramatic supernova, a dazzling explosion illuminating the galaxy. However, for the largest stars, their conclusion can be surprisingly subdued. Certain stars possess such immense weight that upon depleting their fuel, their cores implode, and gravity triumphs with such totality and abruptness that the outer layers plummet directly inward. No detonation, no cheerful goodbye. It was simply an unexpected vanishing. This procedure is referred to as a direct collapse. In an instant, a star vanishes, giving way to a black hole, quiet, unseen, and overwhelmingly dense. Astronomers have observed stars that appear to disappear without leaving any evidence behind, as if the light simply blinked out. It's a reminder that not every cosmic conclusion is marked by spectacular displays. Some are murmurs in the shadows. Galaxies can orbit one another, like moons around planets. We tend to think of galaxies as isolated islands in space, but many live in small groups, where they interact and even orbit one another. Our own Milky Way galaxy, for example, has dozens of smaller satellite galaxies. The large and small, Large Magellanic Cloud are the most famous. These companions move around the Milky Way galaxy like moons around a planet, slowly tracing long elliptical paths through space. Sometimes, larger galaxies pull stars from their companions, forming streams and tidal tails that stretch across millions of light years. Over time, a smaller galaxy may be absorbed completely. These cosmic dances happen over billions of years. Slow, graceful interactions on a scale we can barely imagine. In the quiet of deep space, even galaxies can keep each other company. The universe's brightest explosions come from collapsing magnetic stars. There's a rare kind of explosion called a magnetar hypernova, and it may be one of the brightest things the universe can produce. A magnetar is a neutron star with an unimaginably strong magnetic field, trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy quickly, it can produce a burst of light and energy far more powerful than a typical supernova. These events may be responsible for some long-duration gamma-ray bursts, flashes of high-energy light that travel across the universe and briefly outshine entire galaxies. The explosion lasts only seconds, but its light can reach us from billions of light-years away. It's one of the universe's most intense phenomena, created by a small, dense object wrapped in magnetic fire, collapsing in on itself. The edge of the observable universe is not the edge of the universe. When we look out into space, there's a limit to how far we can see. About 46 billion light-years in any direction. That's the edge of the observable universe. It's not a wall or a boundary. Just the furthest distance light has had time to reach us since the Big Bang, given the expansion of space. Beyond that, the universe likely continues. We just can't see it yet. And because the expansion of space is accelerating, some parts of the universe are moving away from us faster than light. That means their light will never reach us, not even in infinite time. The observable universe is like a bubble of vision, not the full size of reality, but just the part available to us. Beyond that, more galaxies, more stars, maybe forever. Some galaxies shoot jets of plasma for millions of light years. At the heart of many galaxies lies a supermassive black hole, and sometimes, as matter falls toward it, not all of that matter disappears. Some of it gets caught in magnetic fields and blasted outward in narrow, powerful jets, streams of plasma moving near the speed of light. These jets can stretch far beyond the host galaxy itself, reaching lengths of millions of light years. We see them glowing in radio wavelengths, forming enormous lobes that mark their reach. Galaxies like these are called radio galaxies, and their jets are among the largest structures in the universe. It's a strange irony. The most powerful outflows can come from the regions around black holes, where light can barely escape. Even silence, it seems, can leave a mark. There's a star that orbits the Milky Way galaxy backward. Most stars in the Milky Way galaxy orbit in the same general direction, following the galaxy's rotation, but not all of them. There's at least one known star, named Hay 043754439, that moves in the opposite direction. Its orbit is retrograde, cutting against the flow like a salmon swimming upstream. How did it get that way? One possibility is that it was part of a smaller galaxy that merged with the Milky Way galaxy long ago, and its orbit reflects that older, different system. Or it may have been flung into its current path by a gravitational slingshot, perhaps involving a black hole or dense star cluster. Either way, it's a quiet reminder that not all stars follow the rules. And even in the vast cockwork of the galaxy, there are wanderers going their own way. The center of the galaxy smells like raspberries and rum. It sounds like a joke, but it's real. Astronomers, studying the chemical composition of a dust cloud near the center of the Milky Way galaxy, discovered a molecule called ethyl formate. On Earth, it's associated with the flavor of raspberries and the scent of rum. Of course, the galactic center doesn't actually smell. The vacuum of space wouldn't carry scent the way air does. But the presence of these molecules hints at the complex organic chemistry unfolding in deep space. There are alcohols, sugars, and even amino acid precursors in interstellar clouds. It's not life, but it's the kind of chemistry life might need. So while space may not smell like fruit and liquor, it contains the building blocks floating silently between the stars. One galaxy is headed straight for the Milky Way galaxy, and it's already touching. The Andromeda galaxy is our nearest large galactic neighbor, and it's on a slow-motion collision course with the Milky Way galaxy. Right now, it's about 2.5 million light-years away, but that gap is closing. In about 4 billion years, the two galaxies will begin to merge. And interestingly, the outer halos of both galaxies, their vast clouds of hot gas and dark matter, are already overlapping. So in a sense, they've begun touching already. The eventual merger will be more of a graceful blending than a crash. Stars will mostly pass by one another without colliding. Over time, the two spirals will become one larger elliptical galaxy. We sometimes call this future system Milkomeda. It's a long wait, but it's already in motion. A cosmic meeting playing out over billions of years. The CMB still glows all around you. Every part of the universe, including the space around you right now, is filled with a faint glow called the CMB. It's the afterglow of the Big Bang, light released when the universe was about 380,000 years old. Back then, the cosmos was a hot, dense plasma. When it cooled enough for atoms to form, light was finally free to travel. That light has been moving ever since, stretched into microwaves by the expansion of space. Today, we detect it as a nearly uniform glow in all directions. It's not something you can see or feel, but sensitive instruments can pick it up as a kind of cosmic whisper. This glow is the oldest light we can observe. A quiet signal from the universe's childhood, still echoing through space and time. Some supernovae are powered by invisible collapse. Not light, supernovae are known for their brightness, massive explosions that briefly outshine entire galaxies. But not all supernovae are luminous. Some are what astronomers call failed supernovae. In these cases, a massive star's core collapses, forming a black hole. But the outer layers don't explode outward in a visible flash. Instead, they may fall inward, feeding the black hole silently. In rare instances, we've watched stars that seem stable suddenly vanish from view. No explosion, no fading glow, just darkness. These disappearances suggest a collapse so complete that almost all of the energy is swallowed. There's still tremendous violence, but most of it is hidden. It's a reminder that not all cosmic deaths make noise. Some happen in silence, deep inside gravity's grip. There are entire galaxies made mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipticals filled with billions of stars. But some galaxies are barely visible at all. These dim systems contain very few stars, but they still have mass, mostly in the form of gas and dark matter. They're difficult to detect with regular telescopes and often appear only as faint smudges or through indirect measurements. Some of these galaxies may be failed systems, structures that never formed many stars, perhaps because they were stripped of gas or heated too early in cosmic history. Others may be temporary phases in galactic evolution. What they all have in common is subtlety. No fireworks, no spiraling arms, just quiet, gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in cosmic dances. When two black holes orbit one another, they emit ripples in space-time called gravitational waves. As energy leaks away, the black holes spiral inward, until they merge in a final dramatic moment, two invisible giants becoming one. These collisions don't make light, but they send out bursts of gravitational waves that we can now detect on Earth. The first of these signals was observed in 2015, confirming a century-old prediction by Einstein. Since then, we've detected dozens more. Each one tells a story about massive objects colliding in distant galaxies long ago. These black hole mergers happen quietly, invisibly, but with incredible force, converting entire solar masses of energy into waves that ripple across the universe. And for a moment, the fabric of space itself sings. Some stars die in slow motion, taking billions of years to fade. Not every star ends in a sudden explosion. Smaller stars, like our Sun, die much more slowly. After burning through their hydrogen fuel, they expand into red giants, shedding their outer layers into space. What remains is a dense, hot core, a white dwarf. This remnant no longer produces energy. It simply radiates away its leftover heat, very, very slowly. A white dwarf can take billions of years to cool, gradually dimming, until it becomes invisible, a black dwarf. But the universe isn't old enough for that to have happened yet. Every white dwarf that's ever formed is still glowing, somewhere, quietly fading in the dark. The death of these stars is less like a firework and more like an ember cooling gently over cosmic time. Time, near a black hole, slows down compared to Earth. In Einstein's theory of general relativity, gravity not only exerts a pull on matter, but also distorts the fabric of space and time. In regions where the gravitational field is stronger, time flows at a slower rate, compared to areas where gravity is weaker. In the vicinity of a black hole, where gravitational forces are at their peak, this phenomenon intensifies significantly. Should you find yourself orbiting just beyond the event horizon, you would experience time at a significantly slower rate compared to someone situated at a greater distance. Time spent close to the black hole could translate to years in other locations. This is not a work of science fiction. It is an actual, quantifiable phenomenon known as gravitational time dilation. We've also seen it in a less intense manner with GPS satellites. In the vicinity of black holes, it takes on a deeper significance. In a sense, they not only capture light, but they also elongate time itself. The emptiness between galaxies is more frigid than any laboratory found on Earth. The immense voids that separate galaxies, distant from stars, planets, or gas clouds, are remarkably frigid. The temperature in that location falls to merely a few degrees above absolute zero, approximately 2.7 Kelvin. It's more frigid than any naturally occurring location on our planet, and chillier than the majority of settings we can produce, even with cutting-edge laboratory technology. This coolness arises from the almost complete lack of particles and energy. There is no substance to retain warmth, merely a dispersion of wandering atoms and the subtle microwave radiance from the nascent universe. These vast cosmic expanses are the most silent, solitary realms we can imagine, immense and devoid of life. Spanning millions of light years, they represent the universe's profoundest shadows, containing merely the faint echo of creation. The universe is becoming increasingly transparent over time. In the nascent universe, light was unable to move freely. The universe was permeated by a hot plasma, a haze of free electrons and atomic nuclei that continuously scattered photons. As the universe continued to expand and cool, it eventually reached a stage where electrons merged with nuclei, resulting in the formation of neutral atoms. In an instant, light was able to travel freely. This event, known as recombination, occurred approximately 380,000 years following the Big Bang, resulting in the release of the CMB that we continue to observe today. Since that time, the universe has progressively become more transparent. The emergence of galaxies and stars introduced fresh sources of light, and as matter disperses, there becomes increasingly less to obstruct a photon's journey. Over time, the shadows have taken on a more defined shape. Space, which was once radiant and dense, now allows light to flow through with little obstruction. a black hole's shadow has been captured. In 2019, the Event Horizon Telescope unveiled the first direct image of a black hole, specifically its shadow. The black hole remains invisible, yet the luminous ring of heated gas spiraling around it indicates its existence. This specific black hole resides at the core of the galaxy Virgo A, located approximately 53 million light-years from Earth. The image depicts a circular silhouette, an area from which no light can escape, encircled by a halo of radiation distorted by gravitational forces. Years of global collaboration were required, as telescopes around the world coordinated to function as a single planet-sized lens. The outcome transcended mere imagery. It marked a subtle victory for science, allowing us to catch our first sight of one of the universe's most enigmatic objects, not via fiction or speculation, but through illumination. A galaxy is visible to the naked eye from your backyard. Many galaxies are located at such vast distances that even the most advanced telescopes can only show us faint smudges. However, there is one that you can observe without any tools whatsoever: the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it manifests as a gentle, misty oval in the sky, barely discernible to the naked eye. It is located more than 2.5 million light-years from us. The light you observe embarked on its journey long before the emergence of humans. Andromeda is home to 1 trillion stars, which is more than twice the number found in the Milky Way galaxy, and it is gradually making its way toward us. It may be difficult to comprehend, yet you can gaze upward and witness a whole galaxy without any telescope or filter, just the sky, your eyes, and the gentle illumination of something immense and timeless floating in the darkness. A small satellite picked up the faint signal of a far-off black hole collision. In 2015, a small satellite known as Laser Interferometer Gravitational Wave Observatory made an extraordinary discovery, detecting a faint ripple in space-time originating from over 1 billion light-years away. The event was triggered by the collision of 2 black holes, which generated gravitational waves that traveled through the universe. These waves are remarkably nuanced. Upon arriving at Earth, they manipulate space, stretching and squeezing it by an amount smaller than a proton's width. However, with precise tools, we are able to identify them. Laser Interferometer Gravitational Wave Observatory and its companion observatories function as cosmic ears, attuned to the universe's profound vibrations. What they heard was validation of a forecast made by Einstein 100 years prior, that even in the quiet of space, monumental occurrences can emit waves that we can perceive. A solitary chirp from the convergence of unseen titans, detected by a minuscule sensor in a tranquil nook of a little blue world. Certain areas of the universe are moving away from us indefinitely. The universe is growing, and this growth is speeding up. As the universe expands at an increasing rate, certain galaxies are moving away from us so swiftly that their light will never arrive here. Even if we waited indefinitely, the distance separating us from those galaxies would expand too rapidly for the light to bridge the divide. They have crossed a threshold that cannot be undone, moving past the cosmic event horizon. Over time, an increasing portion of the universe will disappear from sight, not due to its absence, but because its illumination can no longer touch us. This isn't something we will experience on a daily basis, but over the course of billions of years, it signifies that the visible universe will diminish. The universe is not only expanding, but it is also subtly releasing its grip. Certain black holes could be primordial, originating prior to the existence of stars. Black holes primarily arise from the collapse of large stars. However, there is an alternative option: black holes that emerged in the primordial stages of the universe, prior to the existence of stars. These are referred to as primordial black holes. They might have originated from small variations in the extremely dense and hot environment that existed shortly after the Big Bang, areas where gravity gathered matter into extremely dense clusters. Certain black holes might be remarkably tiny, Some individuals may have developed and evolved as time has passed. While we haven't directly observed one, their potential existence might shed light on dark matter, contribute to galaxy formation, or provide new understanding of the early universe. They would exist beyond the age of stars, surpassing galaxies, remaining as quiet remnants from the initial moments following the inception of time. Entangled particles could connect far-flung regions of the universe. Quantum entanglement stands out as one of the most peculiar phenomena in the realm of physics. When two particles become entangled, their characteristics stay connected, regardless of the distance between them. Alter one, and the other transforms immediately, regardless of the distance between them. While it doesn't convey information at speeds exceeding light, it does imply that the fabric of reality at the quantum level is profoundly interwoven. Certain physicists propose that entanglement might be integral to the very structure of space-time, potentially contributing to the cohesion of space itself. Particles formed in the early universe might still be entangled today, spanning the vastness of the expanding cosmos. In that case, there could be subtle, unseen connections linking far-off areas, quantum reverberations from the past, lingering in the void between galaxies. Quantum pressure exists in the vacuum of space. Even in a perfect vacuum, devoid of atoms, particles, and radiation, energy still exists. Quantum physics reveals that what we perceive as empty space is not genuinely devoid of substance. Rather, it is characterized by minute, ceaseless variations, with particles and antiparticles emerging and vanishing, fields subtly adjusting, perpetually in motion. This process generates pressure, referred to as vacuum energy. On a grand scale, this pressure could provide insight into dark energy, the driving force behind the universe's accelerating expansion. In contrast to other forms of energy, vacuum energy remains constant, even as space expands. It remains unchanged, expanding space more rapidly as its quantity increases. It's an odd notion that the less you possess, the more significant it appears. The subtle power of void may be the very reason the universe expands. Over the course of trillions of years, black holes emit a subtle heat signature. Black holes are known for their profound darkness, possessing such density that nothing, not even light, can break free from their gravitational pull. However, due to the work of physicist Stephen Hawking, we understand that they are not entirely silent. Quantum theory suggests that black holes have the ability to emit a subtle glow known as Hawking radiation. At the boundary of the event horizon, virtual particle pairs sometimes lead to one particle escaping while the other is drawn in. The escaping particle materializes, a small fragment of energy dissipated from the black hole. Over extremely extended periods, this gradual leakage can lead to the black hole diminishing in size, ultimately resulting in its complete evaporation. For a black hole with the mass of the Sun, that process would require over a trillion years. It concludes in the most subdued manner, lacking any dramatic flair, instead gently diminishing into silence. More plasma exists in the universe than solid matter. Typically, when we consider matter, we envision solids, liquids, and gases. However, the most prevalent state of matter found in the universe is, in fact, plasma. Plasma is a state of matter characterized as an ionized gas, consisting of a cloud of particles in which electrons and nuclei can move freely. It exists within stars, in the solar wind, throughout interstellar space, and even in the immense areas that lie between galaxies. The majority of the observable matter in the universe exists in this form. Plasma exhibits unique characteristics that set it apart from other states of matter. It reacts to magnetic fields, moves like a liquid, and has the ability to transmit electrical currents over vast distances. On Earth, it is seldom observed, except in instances of lightning, fire, or neon lights. In the vastness of space, plasma is omnipresent, illuminating, streaming, and forming much of our visual experience, often without our awareness. Gravitational waves move at the speed of light. Gravity not only exerts a pull, but it also has the capacity to create ripples. When enormous entities such as black holes or neutron stars come together, they generate ripples across the very structure of space-time. As these gravitational waves travel, they stretch and squeeze space, radiating outward in every direction. They move at the speed of light, which is the ultimate speed limit in the universe. After many years of effort, we have finally created instruments that are sensitive enough to detect these phenomena, allowing us to hear the cosmic ripples from our planet. Every wave conveys details about far-off cataclysms, including the mass involved, the speed of the object's rotation, and the extent to which space was distorted. Gravitational waves may not be audible to us, yet they exist, can be measured, and are unexpectedly soft, subtle vibrations within the profound framework of the universe. The vast, large-scale structure links galaxies throughout the universe. Mapping the positions of galaxies on the grandest scale reveals something truly stunning. A vast, interconnected tapestry of filaments and voids, known as the large-scale structure. Galaxies are not solitary entities in the vastness of space. They come together along unseen strands of dark matter and gas, extending like tendrils between clusters. At the intersections of filaments, we encounter superclusters, vast clusters of galaxies. Between them exist vast, silent expanses, nearly devoid of substance. The large-scale structure cannot be observed in its entirety through a telescope, but its intricate structure becomes apparent through extensive sky surveys. It looks like a network, a foam, or the branching patterns found in neurons. The universe takes on a form that is intricate and interconnected, resembling a natural growth rather than a mere construction, revealing its design on the largest scales. The James Webb Telescope is capable of observing galaxies that have ceased to exist. The JWST was designed to observe deeper into the cosmos than ever, and in this pursuit, it also peers further back into the past. Due to the time it takes for light to travel, we observe distant galaxies as they existed billions of years in the past. Some of the galaxies that Webb observes might have ceased to exist in the form we currently perceive them. They might have combined, diminished, or transformed completely. Yet their light continues to arrive, a moment captured in time, still traversing space long after the origin has shifted. This is a rather peculiar aspect of astronomy. Telescopes do not reveal what exists in the present moment. They reveal to us what existed at various points throughout the history of the universe. Each deep-field image serves as a time machine, showcasing a collection of light that has long since disappeared. Far-off galaxies shine with illumination that departed from them long before the existence of Earth. When you observe a galaxy billions of light years away, you're not merely witnessing distance, you're witnessing time itself. The light from that galaxy embarked on its voyage long before Earth came into being, prior to the formation of the Sun, and even before our solar system started to take form. Certain galaxies that we see now emitted their light more than 10 billion years in the past. The glow traversed the vastness of space, elongating and taking on a reddish hue as it journeyed, until it ultimately arrived at our telescopes. In a way, we are observing the ancient history of the universe as it unfolds before us. The stars visible in those galaxies might have already ceased to exist. Their glow serves as a gentle reminder that the night sky is filled with tales that predate our planet. Whole galaxies can disappear behind layers of dust. Even a colossal entity like a galaxy can be obscured by dust. In certain areas of the cosmos, dense clouds of interstellar dust block the light that lies beyond them. This dust is not the same as what you would encounter on a bookshelf. It consists of minuscule particles of carbon and silicates floating within frigid molecular clouds. When a galaxy is situated behind one of these clouds, a significant portion of its light may be obstructed in visible wavelengths. It becomes visible only when we observe it using specialized instruments, such as infrared, radio, or X-ray light, which can penetrate the dust more effectively. Astronomers have uncovered entire galaxies in this manner, hidden behind what previously appeared to be a vacant expanse of sky. In the vastness of space, what you see may not always be the truth. Darkness is not solely defined by the lack of light. At times, it simply involves biding your time until you are illuminated in the appropriate way. Certain galaxies are encircled by flawless rings of lensed illumination. At times, the immense gravity of a galaxy distorts the light coming from objects that are even more distant. When the alignment is precisely correct, this bending results in a phenomenon known as an Einstein ring, which appears as a flawless circle of distorted light. This phenomenon is a type of gravitational lensing in which the mass of the foreground galaxy bends space-time, functioning as a lens for the light coming from the background. Einsteinringe sind selten, aber wunderschöne leuchtende Schleifen, die im Weltraum schweben. Sie entstehen nicht durch Bewegung, sondern durch Perspektive und Gravitation. The illumination may originate from a far-off galaxy, a quasar, or perhaps even a supernova. These rings assist astronomers in measuring the mass of galaxies, mapping dark matter, and exploring the early universe. They exist in silence, flawless illusions, natural lenses formed by the very contours of space. The universe could be boundless. As we gaze at the stars, it's only natural to ponder whether there exists a boundary, an edge to all that we see. However, recent observations indicate that space could potentially extend indefinitely. We are limited to observing just a finite region, known as the observable universe. However, the universe might persist indefinitely. No boundaries, no focal point, merely an abundance of galaxies, countless stars, and endless space. If that is indeed the case, it suggests that a significant portion of the universe will forever remain out of our grasp. We will never witness the entirety of it, regardless of how far we search or how patiently we endure. An infinite universe suggests not limitless possibilities, but rather an unending expanse, a serene immensity that extends indefinitely, softly, and without resolution. Cosmic rays impact Earth from the vastness of deep space. Every moment, high-energy particles, known as cosmic rays, strike our planet, with some originating from the Sun, while others come from far-off regions of the galaxy, or even further afield. They consist of protons, atomic nuclei, and various fragments propelled to astonishing velocities by the explosive power of stars, black holes, or enigmatic cosmic forces. While the majority are redirected by Earth's magnetic field or absorbed by the atmosphere, a portion makes it to the surface, and a select few can even penetrate your body. These particles pose minimal risk in small amounts, yet they serve as a subtle reminder that space is far from empty. It pulses with activity, vibrancy, and unseen signals from distant occurrences. Occasionally, a cosmic ray strikes a detector, revealing a narrative that started light years away, tracing a particle's voyage from a supernova to your sky. It is possible that there was no existence prior to the Big Bang. The expression, prior to the Big Bang, appears intuitive, yet it might lack coherence. Based on general relativity and various cosmological models, time itself originated with the Big Bang. That moment marked not only the emergence of matter and energy, but also the inception of space and time as we understand them today. Inquiring about what preceded is somewhat akin to questioning what lies to the north of the North Pole. Certain theories propose the existence of a prior state or universe, while others depict a quantum realm in which time functions differently or may not exist at all. However, in the majority of models, the time before the Big Bang is not a location we can explore, even in our imagination. The Big Bang did not represent an explosion occurring in space. It marked the dawn of the cosmos. In the past, astronomers confused quasars with stars that were relatively close to Earth. Upon their initial discovery, quasars appeared as faint, point-like entities, strikingly similar to regular stars. However, their light did not act as expected. Their spectra exhibited unusual characteristics, and their brightness fluctuated in enigmatic manners. It took years to understand that these were not stars at all. These were far-off galaxies, featuring remarkably dynamic cores. A quasar is driven by a supermassive black hole, encircled by a rotating disk of heated, descending gas. The gas heats up and radiates with astonishing brightness, at times surpassing the combined light of the entire galaxy. The initial quasars were located at such vast distances that the light from them took billions of years to arrive here. Despite everything, they resembled small stars, an instance of misidentification that ultimately became one of the most significant breakthroughs in the field of astronomy. Our local group of galaxies is moving toward an obscured area. The Milky Way galaxy is in constant motion. It drifts through space, accompanied by the Andromeda Galaxy and numerous smaller companions, as part of a loose collection known as the Local Group. This group is progressing towards something even greater, a gravitational anomaly known as the Great Attractor. Yet, beyond that, there exists an even more enigmatic area. The Shapley supercluster, along with potentially other superclusters concealed by the thick plane of our galaxy. These far-off entities exert a force that we can quantify, even if we have yet to observe all of them. It feels like our whole neighborhood is drifting towards something vast, shrouded in darkness. We are unaware of what awaits us in that direction, merely that we are advancing toward it, gradually, drawn by the force of hidden titans. We are experiencing a vibrant and flourishing season in the universe. At this moment, the cosmos is abundant with stars, igniting, shaping, and bursting forth. This is a fairly new occurrence. In the initial few hundred million years following the Big Bang, stars did not exist. The initial entities emerged from the void, illuminating their environment, and commenced the journey of cosmic development. Since that time, star formation has increased, reached its peak, and gradually decreased. We currently exist in what could be described as a cosmic spring, an era where new stars continue to form, albeit at a reduced rate compared to the past, and significantly more than what will occur in the distant future. Eventually, the final stars will emerge, and following that, the cosmos will gradually fade into darkness. For the moment, it remains a beacon of fresh starts, shining brightly enough to explore, serene enough to pause. In a far-off future, the birth of stars will cease. The process of star formation relies on the presence of cold gas, specifically clouds composed of hydrogen and helium that undergo collapse due to gravitational forces. However, as time passes, this fuel becomes limited. It becomes trapped in stars, scattered by supernovae, or heated to the point of being unusable. In billions of years, galaxies will exhaust the resources required to create new stars. The ones that stay will grow old, wear out, and eventually disappear. Initially, the blue giants, followed by the suns, then the red dwarfs, until eventually even the slowest burning embers fade into darkness. The universe will not come to an end in a single moment. It will gradually fade, softly and subtly. What remains will be black holes, white dwarfs, neutron stars, and the stillness of a universe turned frigid. Not tragic, merely still. The majority of matter in the universe remains unseen. As we observe the universe, including stars, galaxies, and nebulae, we are merely catching a glimpse of a tiny portion of what truly exists. The majority of the matter in the universe does not emit light. It neither emits nor reflects light. The substance that cannot be seen is referred to as dark matter. Even though we haven't observed it directly, we are aware of its existence due to the gravitational effects it produces. Galaxies rotate at speeds that exceed expectations. The light from far-off objects bends more than anticipated. Clusters maintain a cohesion that surpasses what their apparent mass would suggest. This indicates the presence of a concealed mass, exceeding 5 times that of regular matter. Dark matter permeates the cosmos, influencing the very fabric of the universe's structure. We simply cannot perceive it. It serves as a subtle, unseen structure, supporting all that surrounds it. The light emitted by the earliest galaxies has undergone stretching due to the expansion of the cosmos. As light journeys through the vastness of space, it not only progresses, but also elongates. The reason for this is that the universe is expanding, and as it does so, it drags light waves along with it. The light emitted by the earliest galaxies billions of years in the past has undergone a transformation, shifting into longer wavelengths and transitioning from visible light to infrared. The process, referred to as redshift, is a primary method used by astronomers to gauge distance and time within the universe. The greater the stretch of the light, the more distant and ancient its origin. With telescopes, such as James Webb, we are able to observe that ancient light, now gently softened and reddened by its long journey. What started as the brilliance of youthful stars now comes as a soft murmur, elongated by the vastness of the cosmos. The universe could potentially be a hologram. It may seem like something out of a science fiction novel, yet certain physicists have genuinely investigated the concept that our three-dimensional universe could be a projection arising from a more fundamental two-dimensional reality. This concept is referred to as the holographic principle. Research on black holes reveals that the information regarding everything that enters is seemingly inscribed on the surface, rather than within the volume of the black hole itself. Certain theories propose that the universe, in its entirety, could function in a similar manner. What we understand as space and depth might be a form of mathematical illusion, stemming from information inscribed on a far-off boundary. While it may not be substantiated and likely won't impact your daily routine, it's a subtle nudge that reality, even in its most concrete form, might not be entirely as it appears. At the smallest scale, space could be composed of discrete units. At first glance, space seems to be smooth. Even when viewed through a microscope, it remains devoid of content and unbroken. However, certain theories of quantum gravity propose that space might consist of minuscule discrete units, akin to grains or pixels, in a digital image. The tiniest conceivable scale is referred to as the Planck length, which measures approximately 10 to the power of minus 35 meters. At that level, the smoothness might dissolve into something more essential, revealing a grainy, foamy texture of space-time itself. Currently, we lack the necessary tools to observe it or to conduct direct tests. However, if this is indeed the case, then all things, stars, galaxies, thoughts, and even sleep occur not in an empty void, but within a universe that possesses structure at every level. Some stars rotate at speeds that outpace even the fastest kitchen appliances. Certain stars spin at such high speeds that their equatorial regions swell outward, causing their surfaces to merge into a swift blur. Neutron stars, the incredibly dense remnants of massive stars, push this concept to an even greater extreme. A type known as a millisecond pulsar can rotate hundreds of times each second. The whole star, a massive sphere of nuclear material, spins at a speed that surpasses that of a blender blade. These objects release beams of radiation that traverse the sky like celestial beacons, operating with remarkable accuracy. A significant number of them abound in close orbits, with partner stars, drawing in matter and accelerating in the process. They are among the swiftest rotators identified in the universe, as well as some of the most ancient timekeepers, marking time quietly in the darkness. The universe might conclude in a gradual, silent dissolution. Cosmologists previously speculated whether the universe might eventually implode upon itself. However, the current evidence indicates an alternative outcome: a gradual, perpetual expansion. As galaxies continue to move away from each other and the rate of star formation diminishes, the darkness of the night sky will increase. Current stars will extinguish, one after another. Black holes are destined to evaporate. The very essence of matter might undergo decay. The universe will gradually transition into a colder, quieter, and emptier state known as heat death. It's not an abrupt occurrence. Rather, it's a gradual, soft decline. Over trillions of years, the universe will become quiet as energy disperses and formations fade away. It's not the conclusion marked by flames or frost, but rather by stillness. A cosmos that softly breathed life into existence, only to gently fade into silence. Certain galaxies possess superwinds that sweep away stars. In the centers of certain galaxies, particularly those hosting active black holes or vigorous star formation, strong winds can emanate from the core, transporting gas, dust, and even nascent stars along with them. Galactic superwinds have the capacity to extend for tens of thousands of light years, propelling material into the vastness of intergalactic space. They are propelled by radiation, magnetic fields, and the tremendous energy released by supernovae. As time passes, these winds have the ability to remove a galaxy's star-forming gas, resulting in a quiet and red appearance. They assist in distributing heavy elements throughout the large-scale structure, laying the groundwork for future generations of stars and planets. A galaxy functions in this manner, absorbing matter, sparking life, and subsequently releasing into the emptiness. The distant future of the universe is a boundless, shadowy expanse. In trillions of years, the universe will undergo significant transformations. Galaxies will have separated to such an extent that each one will appear solitary in the darkness. New stars will cease to form. Ancient stars will eventually extinguish. Even the dim light of white dwarfs will eventually diminish. What will be left are cold, scattered remnants, black holes, and a faint echo of ancient light. Over incredibly extended periods, black holes will dissipate, and even matter itself might disintegrate. In the end, everything that exists will become particles, drifting through the void, quiet, gradual, and solitary. The future, referred to as the heat death of the universe, is not characterized by a sudden conclusion. It is an expansive, shadowy tranquility, a celestial sea devoid of ripples, breezes, and boundaries. It's possible that we are residing within an immense cosmic emptiness. The cosmos is populated with groups of galaxies, and in the spaces between vast empty areas, known as voids, exist. These voids extend across hundreds of millions of light years and hold minimal amounts of matter. Certain researchers propose that we could currently be situated within one of these voids, an area that is relatively less dense when compared to the average cosmic background. If accurate, this could clarify specific observations, such as the universe's expansion rate or the patterns found in the CMB. Existing within a void doesn't alter our daily experiences, yet it suggests that what we perceive as emptiness could be a component of a grander design, the serene center of a cosmic bubble, softly gliding through an unseen network of gravity. Magnetars possess magnetic fields that are trillions of times more powerful than those of our planet. A magnetar represents a specific kind of neutron star, a compact remnant of a collapsed star, characterized by an extraordinarily strong magnetic field. The magnetic field of Earth is sufficient to direct a compass. The magnetic field of a magnetar is incredibly powerful, capable of erasing data from great distances, distorting atomic structures, or even tearing matter apart. These fields are transient, deteriorating as time passes. Yet during their existence, they generate flares and surges of high-energy radiation. A magnetar flare, even from a distant part of the galaxy, is detectable here on Earth. No laboratory could generate such a level of intensity. They represent some of the most extreme entities in the cosmos, dense and silent, enveloped in an unseen power, akin to stars that have transformed into mere echoes of memory and magnetism. The largest known object in the universe is a massive quasar group. In 2013, astronomers uncovered an enormous formation consisting of quasars, the bright centers of far-off, active galaxies, extending more than 4 billion light-years in width. This formation, known as a large quasar group, is so immense that it tests our comprehension of cosmic uniformity. Current theory suggests that the universe is expected to be relatively smooth on the largest scales, without any structures surpassing a specific size. However, this quasar group exceeds that theoretical limit. It consists of numerous quasars linked across a vast expanse of space, indicating that the early universe might have developed more extensive patterns than previously believed. The debate continues over whether it is a genuine physical structure or merely a statistical anomaly. Regardless, it serves as a reminder that the universe is intricately complex and possibly more interconnected than our models can consistently forecast. Black holes have the ability to warp space, creating a funnel that affects the flow of time. A black hole not only captures light, but also distorts the very fabric of space-time. As you near its event horizon, space curves inward and time begins to decelerate. From the perspective of an external observer, time in the vicinity of the black hole seems to slow down significantly. At the very brink, it nearly comes to a halt. This distortion forms a structure resembling a funnel in the fabric of space, tight, steep, and unidirectional. Within, every route converges at the core, the singularity. As you approach, time and space appear to exchange roles, where inward transforms into a temporal direction rather than a spatial one. Returning is not an option. The distortion of space-time transcends mere metaphor. It's a geometric design, shaped by the force of gravity, inscribed in the very essence of reality. Certain areas of the universe might never encounter one another again. The universe is expanding and accelerating, leading to certain regions moving apart at speeds exceeding that of light. This indicates that no matter how long we wait, the light from those areas will never arrive at our location. The reverse is also true. There are locations where we cannot transmit a message, as the distance separating us is expanding too rapidly. As time progresses, an increasing portion of the universe will drift out of our grasp. Every galaxy will transform into a solitary island, cut off in the vastness of space, enveloped by shadows. This adheres to the principles of physics. No object is traveling through space at a speed greater than that of light. However, space has the ability to expand steadily and inexorably, distancing one part of the universe from another indefinitely. Gold is the heaviest element produced in a star explosion. Gold is rare on Earth, not just in our economy, but in the universe itself. It cannot be produced in the center of a typical star. Rather, it occurs during the most intense events, such as the collisions of neutron stars or specific types of supernovae. In those moments, atomic nuclei are smashed together under incredible pressure and heat, creating heavy elements like gold, platinum, and uranium. These precious atoms are then scattered into space, mixed into gas clouds, and eventually become part of new stars, planets, and people. Each gold ring, every speck of dust, originated from a cosmic disaster, a subtle reminder of turmoil now resting on your hand. In that sense, gold is not just beautiful, it's ancient, it's stellar, and it came from a universe that forges treasure in fire. The space between galaxies expands while light travels through it. When we observe light from distant galaxies, we're seeing it as it was long ago, but also stretched by the space it moved through. As the universe expands, so does the distance the light has to travel, and that means the light itself is stretched. Its wavelength lengthens, shifting toward the red. This is called cosmological redshift. The light isn't slowing down or losing energy by hitting things. The space it moves through is simply getting bigger. In effect, the universe stretches the signal on its way to us. When we see faraway galaxies, we're seeing more than age or distance. We're seeing how space has changed since the moment that light began its journey, a silent record of the universe's steady breathing. There are sound waves frozen into the structure of the cosmos. In the early universe, before atoms formed and light could travel freely, matter and energy were tightly coupled in a hot plasma. In that plasma, pressure and gravity created oscillations, ripples of compression and rarefaction, like sound waves in air. These acoustic waves left an imprint in the density of matter, a kind of frozen echo. Today, we can see that echo in the distribution of galaxies, a preferred distance between galaxy pairs, like a standing wave preserved in space. This phenomenon is known as baryon acoustic oscillation. It's subtle but measurable, a fossil record of cosmic sound, ringing out from a time before the universe became transparent, a wave that never fades, quietly shaping the structure of everything we see. Galaxies can be eaten by larger ones without a trace. In the vast timescales of cosmic evolution, galaxies don't just float alone, they interact, collide, and sometimes devour each other. When a small galaxy comes too close to a larger one, gravity can tear it apart. Its stars are pulled into long streams, absorbed into the larger galaxy's halo, and eventually blended so thoroughly that the smaller system vanishes from view. We found remnants of such mergers around the Milky Way galaxy, stellar streams arcing through the sky, once part of other galaxies. This process is called galactic cannibalism, but it's slow and elegant, not violent, just inevitable. Over time, large galaxies grow this way, not through building, but through quiet consumption. One galaxy absorbed into another, leaving only a ripple in the stars. There are stars that flicker like fireflies in the night. Not all stars shine with steady light. Some pulse, shimmer, or dim and brighten in rhythmic patterns. These variable stars change for many reasons: internal pressure waves, surface eruptions, or eclipsing companions. From Earth, they look like they're flickering gently in the sky, blinking with a slow, stellar rhythm. Some complete their cycle in hours, others in years. These variations aren't random. Many are remarkably consistent, acting like celestial clocks. Astronomers use them to measure distances across the universe. A single flicker, repeated over and over, can tell us how far away a star is, and even how bright it truly is. Stars don't just burn. Some of them breathe. Some black holes wander through space alone. Not all black holes live in the centers of galaxies. Some roam. A black hole can be ejected from its birthplace by gravitational interactions, kicked out of a galaxy during a collision, or flung away by the recoil of a merger. Once released, it becomes a rogue object, moving silently through interstellar or even intergalactic space. These wandering black holes are hard to detect. They emit no light unless they pass through gas or pull on nearby stars. But they're likely out there, drifting through darkness, unseen and unbound. They carry no orbit, no companion, no home. Just mass, motion, and the deep gravity of the thing that fell inward and never stopped falling. Even black holes can get kicked across the galaxy. When two black holes merge, the violent event sends out a burst of gravitational waves. But those waves aren't always symmetrical. If the merger sends more energy in one direction, it can give the new black hole a kind of recoil, a gravitational kick strong enough to hurl it away at thousands of kilometers per second. Some black holes may be flung entirely out of their galaxies, doomed to drift through intergalactic space. Others settle into wide, wandering orbits. These kicked black holes are hard to spot, but astronomers believe they exist. Silent travelers, pushed by the memory of their own collision. Even the heaviest, most anchored things in the universe can be moved by the right kind of wave. Some stars are stripped down to bare cores of pure carbon. When a star like our Sun dies, it sheds its outer layers and leaves behind a core, a white dwarf. Some white dwarfs are made mostly of carbon, and under the immense pressure of their own gravity, that carbon may crystallize. In other words, some stars become giant diamonds. These stellar diamonds are about the size of Earth, but far heavier, glowing faintly with leftover heat. They no longer fuse atoms, but they still shine for billions of years before cooling to blackness. Astronomers have even detected pulsations in some white dwarfs, a kind of ringing, like the sound of a struck bell. A silent, cooling jewel floating in space, once a star, now a crystal of ancient fire. Most of the universe's history hasn't happened yet. 13.8 billion years sounds like a long time. But if you imagine the entire future of the universe, not just tomorrow or a million years from now, but trillions of years into the future, we're still near the very beginning. Stars are still forming. Galaxies are still assembling. Black holes still shine with the heat of falling matter. In the far future, the stars will fade. The galaxies will drift apart, and the universe will grow cold and quiet. But that chapter hasn't begun yet. Right now, we live in a moment of light, a brief, golden season, when the cosmos is alive with motion and change. The past is vast, but the future is bigger still. Supernova remnants keep expanding for thousands of years. When a massive star dies, it goes out in a supernova, a brilliant explosion that can briefly outshine an entire galaxy. But the event doesn't end with the flash. The shockwave expands outward for centuries or even millennia, sweeping up gas, dust, and anything in its path. These expanding shells of debris are called supernova remnants. They glow in many wavelengths: radio, X-ray, visible light, and their patterns tell the story of the explosion. Some form delicate filaments, others turbulent clouds. The Crab Nebula is one such remnant, still spreading outward from a blast that was seen on Earth in the year 1054. Supernova remnants are the slow exhalations of dead stars, still unfolding long after the light has faded. A beam from a far-off star can be bent by just one planet. Typically, we consider gravity to bend light in significant ways, influenced by stars, black holes, or galaxies. Yet, even a planet is capable of achieving it. When a planet moves directly in front of a distant star and Earth, it serves as a small gravitational lens, enhancing and altering the light from the star. The phenomenon is referred to as microlensing. It's understated and uncommon, yet strong enough to uncover planets that would remain invisible to us, even in distant galaxies. A glimmer in the illumination, a soft arc in the radiance, and in an instant, a realm comes to light. The planet could very well be frigid, shadowy, and unseen. However, its presence bends the starlight just a bit. The twist reveals that the universe once radiated a stunning orange light. In the initial moments following the Big Bang, the universe existed as a hot, dense plasma, radiating with brilliant light. However, as it grew and cooled, that radiance changed. As the temperature fell to approximately 3000 degrees Kelvin, the initial atoms came into existence, allowing light to move unobstructed. In that instant, the cosmos would have appeared orange, contrasting with the blue-black of the night we observe today, instead radiating a gentle, warm glow that enveloped the entirety of space. The light has been stretched by the universe's expansion into the faint microwave glow we observe today, known as the CMB. Once upon a time, the cosmos radiated a warm orange hue, as if illuminated from within, a gentle ember slowly dimming into the annals of time. Certain regions of the universe are experiencing a slower cooling process compared to others. As the universe expands, it cools, slowly and softly, akin to a grand oven being switched off. However, not all areas experience cooling at an identical pace. Certain regions, containing greater density or captured light, hold on to heat for an extended period. For instance, clusters of galaxies hold hot gas that stays warm for billions of years. Some areas are more secluded and cool down at a faster rate. The variations in temperature influence the formation of structures, the evolution of stars, and the duration of specific processes. In a universe defined by straightforward principles, one can still observe local differences, warmer areas, gradual declines, and minor pauses in the vast progression. The universe does not cool in a mechanical manner. It cools with a sense of weather, marked by unevenness, texture, and a subtle vibrancy. One day, we could witness the emergence of a new universe. Certain cosmological theories propose that new universes might emerge within our own, branching off due to quantum fluctuations, black holes, or other mechanisms that remain beyond our current comprehension. If this occurs, it would probably take place at a considerable distance from us, out of any observational reach. However, in theory, one could potentially observe the signs, an unexpected, growing sphere of novel physics, breaking free from our known reality. It remains uncertain whether this has occurred before. It's uncertain whether it ever will. Yet, the concept persists that in some distant time and place, the serene void of our universe might bring forth something entirely novel. A start within a conclusion. A soft murmur within the stillness. The universe continues to resonate from its initial beginnings. In the initial moments following the Big Bang, the universe underwent a rapid and explosive expansion, a phenomenon referred to as inflation. The sudden surge of movement created ripples, small quantum fluctuations extending throughout space. The ripples evolved into the foundational seeds for all subsequent structure. Celestial bodies, luminous spheres, cosmic orbs. They also left behind traces. They appear in the CMB as fluctuations in temperature. One day, we might be able to detect them as primordial gravitational waves. Subtle, steady beats, woven into the very essence of space-time. The cosmos might appear serene at this moment, yet it holds within it the echo of that initial pulse. Like a bell that continues to resonate gently, long after it has been struck, the cosmos is immense, and you serve as a means for it to understand its own existence. Among the many peculiarities in astronomy, one of the most subtly remarkable is this: you are composed of celestial particles. The carbon in your body, the calcium in your bones, the iron in your blood, all originated from stars, dispersed throughout the cosmos, and brought together to form life. You are interconnected with the cosmos. You are a conscious moment of it, a brief moment of consciousness in a cosmos that merely shifts, ignites, and chills. In this regard, the universe has developed a vision, and through those eyes, it gazes back at its own reflection, marvels at its own existence, visions of its own essence. And even now, as you gently slip into slumber, it continues to dream. I appreciate you taking this moment to journey through the cosmos alongside me. We have journeyed across immense expanses, beyond fading stars and emerging galaxies, attuning ourselves to the vibrations in space-time and the reverberations from the dawn of existence. And amidst it all, beneath the glow of timeless stars, in the stillness between galaxies, in the gentle sparkle of dust, there existed you. Inhale deeply and exhale gently. Ideas becoming gentler. Perhaps they are already in a deep slumber. This universe brims with activity and enigma. However, there is also a sense of stillness. It retains warmth, illumination, and gravitational force. However, it also embodies tranquility, the ability to understand it, piece by piece, in tranquility and stillness, is genuinely remarkable. Wherever you find yourself at this moment, whether you are completely alert or gently floating into the realm of dreams, may your slumber tonight be peaceful. May your body find peace like starlight dancing on water. May you hold on to, even if just a whisper, the recollection of a universe that shines, not only above you, but also deep within you. If you're still awake, feel free to watch the next chapter now. If you wish to immerse yourself in more softly narrated tales brimming with wonder, think about subscribing. There is always something new to discover, one drowsy spirit at a time. Sleep well, and as the final truths about life on Earth gradually come to a close, I want you to remember something educational yet gentle. Life wasn't built to rush. From the first single-celled bacteria to modern humans, all life forms thrive on a balanced rhythm of activity and rest. Even the cells in your body only recover regenerate, and retain information best when you're in deep sleep. For me, understanding life has brought a new value. Stop treating myself like a machine. Biology teaches that fatigue isn't a personal fault, but an intelligent signal from the nervous system. By accepting that, I learned to listen to my body, allowing myself to slow down without feeling guilty. It's a very practical scientific lesson. Live in harmony with your own biology, to survive longer, not to burn out. If these perspectives make you feel better, don't forget to subscribe and stay with Sleep Science Top 1. On this channel, we transform scientific knowledge about life into relaxing moments, helping you understand your body better, appreciate the natural rhythm of life more, and sleep more soundly each night. Now, let all your systems rest. Wishing you a peaceful night and a deep, natural sleep, just like life itself on this planet.